Alright, for the third time, welcome back. And you might be wondering what this equation right here has to do with modern logarithmic equations. Because 100 quantity 1 minus 0.1 to the power of x is not a logarithmic equation. Actually, it's an exponential decay equation. Well, the answer is pretty simple. It's because, as we know, the modern logarithm's definition is the inverse of exponential equation. Base answer power and all that jazz. Well, the inverse is just when the output of a function is equal to the input of a separate function. And this is our table, our input and our output. For the logarithm, it's just swapped. Our input becomes our output and our output becomes our input. Now, this isn't how Napier wrote it in his book, Medifici Logarithmoris Canasis Descriptio, but this is why it's named a logarithm, because this column is still called the logarithm, and this is called the arithmos. If you look at a modern example of a logarithm, you might notice it's reflected across this axis. Y equals x. To the power of x is our red equation, and log base 2 input x is our blue equation. You might notice our inputs and our outputs are swapped. 0 is corresponding to 1, and over here, 1 is corresponding to 0. 1 corresponds to 2, 2 corresponds to 1. 2 and 4, 4 and 2. 3 and 8, 8 and 3. 4 and 16, 16 and 4. 5 and 32, 32 and 5. The reason we call it the logarithm, instead of just making up some name for the inverse of an exponential equation, is because of the history behind it.